Example 2.4, a 10-gram block with charge 0.8 microcoulombs is placed in an electric field with components of EX 3000, EY 600 newtons per coulomb. What is the electrostatic force on the block, magnitude and direction? If the block is released from rest at the origin at time t equal to 0, what is its displacement after 3 seconds? So let's draw a picture of this situation. So this is really a mechanics problem, kinematics and Newton's second law. But let's draw a picture. We have a charged block at rest at the origin when a sudden electric field is turned on instantly. So picture-wise, I imagine that I have a block. Let's say that this is my block right here. And I'm going to say that that's my origin right here. And I know it has a positive charge. So you can imagine I'm going to set up an axis that's going to read my y-axis. And then I'm going to have my x-axis. So when I look at the electric field, there's two components that are going to act on this. One, I'm going to have an x component that's 3000. So I'm going to say that 3000 is about 3 squares. So now I've turned on a field in the x direction that has 3000 newtons per coulomb in the x direction. And then the other one has only 600, so that's about half a block. So I'm going to say that this is about like this. So this would then be EY, which is 600 newtons per coulomb. So now I have my field here. So the field direction has to be the same as the force direction, which has to be the same direction as the acceleration. But we want to calculate the electrostatic force here. So let's go do that. So this electric field will produce a net force, and that net force is then going to be equal to the charge times the electric field that causes the charged block to accelerate. And it should follow the direction of the net electric field as well as the net force. The net force will have components given by the net force, and that will have components x, components y, with each of these having been multiplied by the charge to get that. So just to give you a sense of this, if it's 3000 to 600, we could see that the strength of the field and therefore the strength of the force is 5 times greater in the x direction than it is in the y direction. So when we look at its position or displacement, it should be roughly 5 times larger in the x direction than the y direction. So now we have this thing here. So now let's compute these components. So I'm going to get that the force in the x direction is going to be the charge times the electric field. Now they're telling us that I know that the charge here is 0.8 microcoulombs. So if I start putting in my numbers here, this will be 0.8 times 10 to the minus 6 coulombs times my 3 times 10 to the 3 newtons per coulomb. And of course, you see immediately the cancellation of coulombs. And that's going to give me a value of 2.4 times 10 to the minus 3 newtons. And I'm just going to repeat the process for the y component. So if I look at the y component, it's going to be given by this, but we already know what the charge is. And now the force, the field we saw here was 600. So I'm going to write 6 times 10 to the 2 newtons per coulomb. And you'll see that this number will then give me 4.8 times 10 to the minus 4 newtons. So this guy is f of x, this guy is f of y, which we're going to need to calculate the acceleration. So let me just move this over. I can make a nice box. And so I have this right here. So now I have to calculate the magnitude and direction of this force here. So the magnitude and direction of the net force is then going to be like this. So I'm going to say that F net has to be Fx squared, Fy squared, square root. We have those numbers. So if you plug them in, you should get 2.45 times 10 to the, what did I get? I got 10 to the negative 3 newtons. And if I calculate the direction, I'm going to get the tan inverse of Fy over Fx, and that should give me a value of 11.3 degrees, excuse me. So now that I have that, I've now determined the net force. So now if I go to B here, it says here, so we want to calculate the displacement of the charged block after 3 seconds when starting from rest. In order to do so, we need to calculate the accelerations because there's a net force acting on it via Newton's second law. So if I do that, then that just means that the acceleration in the x direction divided by the mass, well, this should just be 2.4 times 10 to the minus 3 newtons divided by 10 times 10 to the minus 3 kilograms, and I'm going to get 0.24 meters per second. And if I repeat the exact same calculation for AY, then I'm going to get 0.48 times 10 to the minus 3 newtons divided into 10 times 10 to the minus 3 kilograms. And I end up getting an acceleration of 0.048 meters per second squared. So I now have my accelerations. So now I can use kinematics to determine the displacement. So using kinematics, to calculate the displacement I will set up two tables to organize the information. So what do I know? I know that this is what we are looking for, delta x. I know the acceleration in the x direction, which was 0.24 meters per second squared. So that's my acceleration in the x direction. I have the final velocity and I have the initial velocity, but we know that it's starting from rest and we're looking for the displacement after 3 seconds. So all I have to do here is that because this is a two-dimensional motion problem, I have to do the exact same thing for the y. So if I copy this and I just paste this over here, and then I just have to modify this slightly. So when I look at this, I don't care about x now. I only care about y. And so I'm going to come in here and I'm going to say y, 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 y. It starts from rest, and the acceleration in this case is 0.048. So the one thing that we don't have is we don't have the final velocity in the x and the y direction. That means that it's these unknown quantities that we don't have that tells us how to choose the kinematic equation. So from here, this tells us that we choose equation delta x equals to v initial xt plus 1/2 axt squared. And the same thing happens with the y. So now that we know the equation, we can calculate displacement. So calculating the components of the displacement, I then have that I have delta x, the initial speed is 0, then I have 1/2 axt squared, and then I'm just going to punch in my numbers. So this is going to be 1/2, and this has an acceleration of 2.4 meters per second squared. My time is 3 seconds squared. And so when I compute that, I get 108 meters. Now, if I repeat the exact same calculation for the y, you're going to get a value of 21.6 meters. So now I know the components. I can calculate the displacement. The displacement is then going to be given by delta r, which is the square root of the sum of the squares. So then if I enter this, that's 108 squared plus 21.6 squared square root. And if my numbers are clean, it's going to be about 110 meters. And if I look at the direction of this thing, remember, it should be the same direction as the force, same direction as the electric field. I should be able to just write 11.3 degrees. But you don't have to trust me because we could calculate this. And if I take the tangent inverse of 21.6 divided by 108, I also get 11.3 degrees as expected.